Hello and welcome to another episode of trying to teach you some C programming like the good old days. And you want some nuts? I have them in here. Catch them. Now we're going to be starting off with the preprocessor commands that are available for us in the conventional C compilers. I cannot write that down. The preprocessor macros in C. And once again, we're going to be listing them out online so that you can learn to research while learning to program. And the websites we send you through assignments and showing you in lectures are not arbitrarily chosen. They are the ones that we want you to learn, that we want you to be aware of, so that you can reference them in future, because they're good websites and ones we regularly use. And we call so a compiler and an interpreter. Let us write these down as well. They are programs. They're responsible for running programs. What do we mean by that? And actually, we can add the assemblers as well. Compilers and interpreters and assemblers are programs that are responsible for executing or making the code executable to the computer or executing them. Because, for example, when you write in C or Python or some other language, you create some sort of text file that is meaningless to the CPU. You know, the CPU would take that, try to do something with it, but it cannot, because the CPUs are designed to take fetch instructions that are encoded in binary and that which has to match their previously recorded table of possible instructions that they describe in their manuals when they're manufactured and when they're designed. But they have specific kind of pre-coded instructions that you have to give to them in order for them to do something. Other than that, they will not do anything. So these texts can include these pre-encoded binaries, because all of these are stored in binary format in the computer. They're all represented by ones and zeros. They're all electricity inside of your computers. They may represent something meaningful to the CPU, but they would most certainly, almost 100%, never ever represent what your program is intending to do. So we have to convert these into some binary format in order for the CPU to be able to run them. And that nut is crazy. So in order to do that, as we've discussed in the previous lectures, we first had, I keep forgetting the name, but I'm gonna write it in Turkish. Search it first, and then look for Wikipedia to translate it for me, which is punch tape. We first introduced punch tapes, which encode binary in the simplest format, and when the CPU patches them through some special circuitry and electronics, it is able to distinguish between ones and zeros encoded on this tape and act accordingly. Then we proceeded to use some text-based languages, because it is easier to write in some text-based language than with, say, punching holes in on a paper, as we've seen in the punch tape just at the moment. So people came up with new ways to program a computer, and by programming a computer, we mean giving it a program. And a program is basically a list of instructions and data for these instructions to act on, to be wholly executed by a computer. And by a computer, we mean, as we've discussed in the first lecture, the von Neumann architecture, which is a CPU, a central processing unit, and a memory, which is in today's computers is mostly RAMs. And the CPUs in today's computers are actually not the CPUs mentioned in the von Neumann architecture. We have built abstraction layers upon abstraction layers over what we have designed previously over decades ago. We now have several central processing units embodied with memories packed into cores which make up today's processors, and then accompanied by another outside RAM. So the architecture today is a bit different, but the fundamental concept is still there. So to be executed by this architecture, we need to encode these in the binary format once again. So in order to do that, we came up with text-based languages, and first was, I guess, assembly. And assembly, as you know, is just writing all of the CPU CPU code, CPU instructions, which are these. I'm trying to be showing you. You know, for the CPU, it is literally lines of these. You know, lines and lines of these. These operations are usually divided into two segments. The first half represents the actual instruction, and the second half represents the argument to be given. Like, for example, add, and then 1 and 1. For example, add 1 and 1 to themselves and put it on some register. It is encoded in the CPU. But assembly language is actually just a converted version of that into text. Literally, there's almost no difference. And once you change the text into their corresponding binary, it is almost the same with the normal binary program. There are some, of course, abstraction layers built up on top of that over the years. Sectioning the programs, defining macros and functions and stuff, which made the assembly less like the final binary executable. As you know, we started to divide the assembly file into sections, which would then be in the linking phase, the ending phase of any compilation, any converting to machine code process. They would be switched places in the final executable, because we want for example, the data section to be on top and the code section to be at the bottom of the final executable file. These standards are defined by the CPU architectures. We have to obey that, but for conveniency in our code, we write them at the beginning, we write them at somewhere else in our code, maybe in some other file, and the final phase of compilation, which is linking, takes all of them together and then switches places accordingly to the target CPU that it is compiling to. So over the years, assembly evolved into something more or less like the binary file, but it's still pretty close to it compared to the compiled languages, which include C, C++, C#, all of the C family, probably. Like Rust is becoming popular. Go has been popular for 2 decades, I guess. But as people, we all know that all of these languages are false, and we only use C because it is the only acceptable language other than the assembly and the bare-bone binary encoding to be used in any programming and computation task. We all know that deep down. Why cannot I open that image in a new tab? Oh, whatever. The compilation process is very similar to very similar to assembler process. It is first taking the code, converting into assembly, and feeding it to some assembler, which then takes it and converts it to the binary, and a linking phase is called at the end as well. And this linking phase is more general than you might think. You may have seen only programs written only in one language before, maybe, but most projects in today's world are written in various languages, like combining assembly, C, Python, JavaScript. All of these unrelated languages may be smushed together in a project. And the linking phase is actually a general process which takes the separately compiled files of each language at the end of the compilation process to smush them, to combine them all into one executable final file. Okay, like for example, your Far Cry 4.exe is the end of many languages compiled object files. We call these compiled files. only compiled files, not linked to any specific library or anything to any other file, object files we call them. But other than that, all the compilation processes are completely separate from each other. Each language is compiled by its own compiler. It is first divided into tokens in a phase called lexing, and tokens is only, like let's write some code. What the hell? Elektrik mi gitti? Sait. Elektrik mi gitti, sen mi kapattın? Now, let's write some code here. The lexing process will yeah. The lexing process will say, yeah, we have a token here, which is a name. I don't know what it refers to, but it's a name. It's the name of a variable, a structure, a function, whatever. I just know that it is a name. Then we have a parentheses. Yeah, the compiler says we have a token of parentheses, we have a token of quotes, we have a token of text, and then we have a token of quotes, and then we have a token of parentheses, and then we have a token of semicolon. So it's just tags the objects by their type. The lexing process does this. And I guess before the lexing or after the lexing, I don't remember that, but we have a stage called pre-processing, and I guess it is before the lexing page, so I forgot to mention it. But it executes these macros we're going to be talking about in a minute before lexing the program, so that it would lex these the code included in these macros as well. And we would see that there are other types of macros other than including libraries and stuff, which are to be which have to be pre-processed before being lexed as well in the code. So we have to be aware of that. And after lexing, we have a process called parsing, which is just taking the tokens produced by the lexer algorithm and making sense of them. Like, for example, the parsing algorithm would say, I guess, yeah, the printf function, I know that it's a function. The name printf is a function, not the name of the variable. It's the name of a function, because I've seen it before declared in some of these files. Maybe you have to declare it, as before doing something with functions or variables, and you can declare it while defining it as well, so there's no problem with that while initializing as well. But the compiler would know from your first declaration, whether it is initialized or defined or not, that printf was a function declared before coming to that line, and it would tag that as a function, and it would produce some kind of internal representation for saying that printf is a function, and takes the arguments in a type called char array, and the parentheses would work for that, and then semicolon marks the end of the code. So a parser would do that, pass it into assembler. The assembler would take the internal representation and change it into assembly. Literal assembly would reside in your RAM, and then finally an assembler would come and change that all to binary code that is compatible with your target architecture. You may be compiling for some other platform or CPU or operating system in some other platform. We call all of these, sets of operating systems and hardware platforms, by the way. You can compile for a platform in a different platform than that. And finally, when it produces the assembly, the linker would come, and the linker would, as we've said, first change the sections, because as we discussed in the previous lecture, the last week, we have to obey the memory segmentation rules. So we have to place the code at the bottom, we have to place the uninitialized and initialized data before it, and then before it, we have to make use of the stack and heap, which are for respectively the local function variables and the allocated, consciously allocated variables inside of the program, the programmer do. So we have to obey that rule. Also, we have to, most importantly than that, include references by either statically or dynamically linking to the libraries that we have specified at the beginning of our file to be included in our program. So linker does that. And as we've said, and again, the linker works generally for all of the compiled source files. So you may think of them as, first generating source files in binary separately for each file, and then linking comes at the end and, links them all in one file. So, you would, let's say, have 12 source files, code files in your project, and then before the linking phase, you would have 12 object files, which are binary files that are not linked, and then you would have one at the end of the linking phase. So this is a basic overview of how compilers and assemblers work. Incorporating interpreters into that, the difference between interpreted and compiled languages is that interpreted languages are never converted into machine code, and instead they are executed by another program. Until the parsing stage, they're mostly the same with the compiled languages, but after the parsing stage, instead of turning the internal representation into assembly, the interpreter of the target language, which may be Python, JavaScript, Ruby, it takes the internal representation and does whatever it says. It acts like a CPU. It is programmed by the program. The interpreter is programmed by the program, and it does whatever the hell the internal representation, the parsed language says it to. It executes them. And there's no linking, of course, because the import segment, for example, in a Python program, which says a Python interpreter to use some other file instead of the main source file we're executing at the moment, the Python interpreter would see that and would look for functions and classes and variables inside of this file. And when called in the main source file, it would use them. So there's no requirement for pre-processing or linking. It just execute them. And you might ask how we would incorporate all of these into a compiled project. Well, you would call the scripts. We call these scripts, by the way, Python programs and JavaScript programs. You would use specific system calls, which are used to normally run programs. Like, for example, you are using Firefox and you want to open a PDF in your PDF reader. The Firefox executes a specific code from the standard library that says the operating system to open a specific program. Using the same function, the compiled program would call the operating system to execute some script, some Python or JavaScript or Ruby or shell script, maybe. As we've said, shells are languages too. It would tell the operating system to execute these, and these programs would normally have some defaults assigned to them by the operating system, or they would have shebangs at the beginning of the file that says which interpreter to be used to execute this file. As you can see, I'm using the term execute because these scripts are said to be executed by their interpreters. So interpreters actually run these programs, execute these programs. So you are telling inside of your compiled project somewhere to execute these programs. And if you are not specifying to operating system to execute them with Python, like you're not explicitly saying Python like lecture.py, which is not present, but you may assume that it is. You are not saying to operating system that Python lecture.py, but instead you're just saying lecture.py, and operating system would interpret this to be a normal program, because when running a program from the terminal, you're not telling something, you're just saying its name, just expressing its name. And this is a program from our previous lectures, by the way. You're just saying its name to the terminal and it executes it. Same thing with the Python program. You would not have to write the Python keyword before it. You just write lecture.py, and if it has the shebang at the beginning of it, would know which interpreter to use when executing these, okay? So this is as basic as that, and then we can come to the processor macros. We of course have includes these parentheses, angle brackets, they say, are used for standard libraries, and codes are for our own files, and we have to specify the path to our own files because, yeah, this is not specified because it's in the same path in the same directory as my source file. But if it was, let's say in some other place, like I can create a lecture.h in this path, in this directory. The topics is a directory in my computer. You have to be familiar with the concept of paths. If you're using Windows, you have C colon backslash and then user and then backslash and then your username and then backslash and then desktop for your masaüstü for your desktop. And in Linux, we also have paths, and in Mac as well. Mac is similar to Linux because they all follow the Unix standards. Windows doesn't. But so if my header file is in some other place than my source file that is including it, I have to specify where it is. And these two dots, by the way, the directory names are separated by slashes instead of these backslashes, which are Windows used in Windows. In Linux, Mac, we use this. And pretty much all of the making sense operating systems, we have to specify the path. Instead of using this, we could also write the path from all the beginning, like say home/sys55, which is my username, /desktop/sty, all of these directories here. But this would not be modular, as this source code can be downloaded into some other computers, and they would not have the same directory structure there, and you would not want any downloading user to having to change any part of your computer. Okay, that is not what you want. You want a modular program, so we might as well include stdio.h here and then define a function, like just a function called add, which adds two numbers. It's for the demonstration purposes, of course, and we return the edit versions of these, save the file, and then we call it here. Yes, no, this one extra disease. We run this. Do not be concerned about what I'm writing here. I'm just trying to run this, compile and run this program. Take that out. And as you can see, we have executed this function right over here. But if we did that, if we remove the path, it's already giving me an error here, lecture.h file not found. But if I try to compile it, it would say no such file or directory called lecture.h. So we have to specify its path when calling our custom libraries. Other than that, we have define, of course. We have this syntax for the define, which I will not go into deep, but it basically is like, for example, you define the define kind of like a function. It, of course, when the preprocessor executes, it replaces this square 4 with not the result of this, but just in parentheses 4 times in parentheses 4. It just replaced this expression with this, as in the usual define, but it acts the x as a variable. It is pretty good for compilation performance purposes. Like, for example, this function we have from the stdlib, I guess, and which we use a lot, would say if our string consists of alphanumeric characters, which are letters and numbers. It is a macro defined in the stdlib, I guess, library to say from the performance. It just replaces all of this with a long expression that at the end tells whether it is the string is alphanumeric or not. But it is a macro. It is not a function that we're calling, because function calling is a performance requiring process. Avoid them as much as possible as not to make the program non-modular. Function calling requires stack, requires a lot of new variables, requires a lot of new CPU calls. So try to avoid that while not, trading off modularity in your program. We have if def and if not def, which we used previously. I can say here, if I ses azaltayım mı? Ses azaltayım mı? Ses azaltayım mı? Bilmiyorum. We can say define win32. We do not have to specify a number here, although we can. And if and def is short for if not defined. And if we did not define it using this syntax here, the preprocessor would do this. And then if we did define it, it would do this. It is the same logic with the if-else conditions in our programs, but it is for the preprocessor. And you can see already that since we defined Win32 here, which is normally not defined in the Linux system, because it is defined in the purpose of signaling the compiler that this is a Windows machine. At least the target is a Windows machine that we're compiling for. The Clang already gives me an error in this Vim that Windows.h is not found. So it knows that it is defined, so it skips these, and once it sees that Windows.h is not defined, it says that I cannot compile that. So this is some little thing, and we've saved it. You see the error away. We have more macros actually, not limited to these. We have a lot of macros in the GCC and CC, the C compilers, and you can find these in this what can I say, in this website over here, but we're not going to be going more deeper into that. Yeah, you can see the list. Elif, of course, we have to have a Boolean expression after that, and elif def is short for that. And by the way, we also have if, else, undef, undefines. We have what did this do? I remember using this, and I remember it being pretty good one, I guess. And I guess it did something like you are including some library in several files. Like for example, I'm including stdio.h here and here to save time in compilation, and sometimes some errors. Save from some errors, we do pragma instead of include at the beginning of this, so that if the compiler checks whether stdio is included somewhere before in some file that is in the scope, the term scope we'll get into a little bit later, in the scope of the current compiled file, it would not include that. And the scope just basically means the set of libraries, functions, variables, structures, and unions and enums. Unions and enums we're gonna see in the later lectures, that the current program is able to access, or the current part of the program is able to access the names the current program recognizes, you might say. Okay, we have warning. I don't know what this means, an error in line. We can have a look at them in more detail, but we don't have to. So we have a keyword called extern. Before that, we have to talk about the concept of scope, what a scope is. In your regular program, like here, for example, in your int main, you're calling the name printf. You're calling this. But how does the compiler know that there exists something like that? Or, in here, before in here, if I am not, by the way, why do we include that? If we remove this, it would not be able to recognize the printf. Why is that? The answer is very simple. We just haven't linked to it, and the program does not see this because it is not in its defined array. You might think of all of these names, the variable names, the function names, the structure names, all as names, as we've said from time to time from the beginning of this lecture. The program does not know that name. It does not recognize it, but because it has not been defined before. Up until that point, we may be defining it after the printf here, but it is not defined before here, because the compilation and interpretation and assimilation process works from the beginning to the end. Like, for example, I can include stdio.h here, but the red mark would still be there. And if I do this, it would be gone because I included that off before calling for printf. So you might say that printf currently is not, while compiling this line here, is not in the list of recognized names for that program, for that part of the program, by the way. And you would be correct. And this idea is called with the name scope. Scope means for a part of the program, the names that this part of the program can recognize and do something with. Like, for example, this part of the program recognizes what? It recognizes the things in ctype.h, in stdlib, in lecture.h, and if you're not compiling for Windows, in onist.h, and nothing more. Okay, nothing more than that. The program does not know anything about these, about anything other than the ones included in this, and of course the standard keywords and other things in the C programming language. So we call this the scope. Why do we make this such a important topic? Because it is more complicated usually than these, especially in the multi-file projects. Like, have you ever thought about why? Like, let's just write a function here. I don't want to spend time writing a function, so let's just do this and return a minus b. And let's just do that. Okay. So why? By the way, this is not true, right? So let's do this. Adder. I guess this works. And we have to cast that into int. The whole expression into int. I guess this would work. And now the variable sign, of course, this expression is a Boolean expression, so it returns a Boolean, which is either 1 or 0. Booleans are not true and false. It is either 1 or 0, and when we convert this to integers, we get the sign of the expression, that is a minus b, and then at the end before returning it, we multiply the a minus b by sign, so it is always giving us the positive result. Okay, so the sign variable here exists only in the lifetime of the execution of the abstract function. When we call the abstract function somewhere else in the program, the sign variable, as we talked about in the previous lecture, comes to life in the segment of the RAM called stack. It's, is giving birth to it. It is now alive. There's something called sign, and we are able to access it. And after this function returns, it is gone. It is deleted from the memory. So there's nothing called sign. So the scope of this function includes the name sign, but the scope of the function main does not include the name sign because it does not have that in scope. The name sign is defined as a local variable inside of this function, and it is only accessible from within that function and dies whenever it is, it is dies whenever the function exists, and it is recreated whenever the function is recalled. So it does not preserve its value from the previous invocation of this function. So it is only limited with the lifetime of the calling of this function. This is what we call a local variable. What we call a global variable, and by global variable, you have to understand that I'm talking about all of the names, so we can have a name for the function, structure, enum, union, which we're going to be seeing in the later lectures. We can have a variable called sign here, and main function would also be able to access it because it's a global variable now. Okay, so this was a local variable that is inside a function and only accessible from within that function. And this is a global variable that is accessible from everywhere if it is inside of this file. We also have another scope that is called the external scope. I'm talking about C, by the way. The rules may differ from language to language, but the concept of scope exists in all of them, of course, because it's essential. There's also an external scope that allows us to use the names from other files. We're going to be getting into that in a minute. And this is a global variable. It is available for the lifetime of this program. Its value may be changed by the app subtract, and it would be readable from the main. The change would be readable from the main, and vice versa. So we can have something like, we can have something like this. We don't have to use the value. Then we can have something like this. Of course, I have to end it and have to pass the variable sign and then copy that and then do something like this. And you will see that the variable sign is manipulated by abstract, and the main is able to see what happened to it. Okay. Okay, I think we made a mistake here. So let me just quickly resolve that. I guess this works. Why did you not warn me? A minus B is less than 0. No, this does not work. All right, I might not think about it. I'm just gonna do this. I wanna think about it. I just okay. And as you can see, it was -1 and then it was 1. The sign variable is accessible from every function because it's global to that file. Any function from that file can access it. But if it was local, which means it would not be by just deleting the declaration from the global scope and placing it inside of this function would make it local to that function and would be inaccessible from elsewhere. And C does not support what do we call it? Functions inside defined inside of the function. So we have no other scope than local, global, and external. And as you can see, it gives an error once I try to compile it, that a variable called sign, a name called sign actually, use of undeclared identifier sign, a name and identifier called sign does not exist. So it works as so. The local variables are accessible only from within that function, but the global ones are accessible from everywhere inside of this file. And to make a variable or a name global, you have to just declare it in the global area, which is outside of any braces. And once you enter a brace, it would be a local scope. The distinction is like so. And you only have to declare it at the global scope. Other than that, you can initialize it. You can define it elsewhere. You have to just declare it in the global scope, and it would be available for all the functions. You don't have to initialize it. Initialization means assigning the first value to it. Declaring it means just saying that something called like this exists. And what what does the define mean? Let's see, I forgot. Okay. I guess defining and initializing is the same, as far as I remember. It's not a pretty important distinction, but I want to address it. I guess we will have to just remove the word define and not confuse ourselves with it. Just know the name of declaration and initialization. I guess definition was something else. So declaration means there's something called that. Like for example, there's something called A. This is declaration. We declare that there's something called A, but we don't have to do anything with its value or what is stored in it. And initialization means giving its first value. And some variables have to be initialized. We will see more about that in the arrays and pointers to section. Not your regular variables. Your arrays have to be initialized sometimes, but we're not going to be concerning ourselves with this in today's lecture. And one more thing about functions, that functions are, when declared at the beginning of a file, like for example, we said that you can do this in our previous lectures, you can do this, it would work just fine. You can declare, and then actually, I guess the word definition meant that you declare a function here and then you define it here. I guess, yeah, that was the distinction. Defining the keyword is like initialization for functions, whatever, and structures and enums and structs and enums and unions. So we can have this declaration and then we can define the function elsewhere, actually after it is called here. And it would not be a problem. And it would also be of no problem to not say these, its arguments as well. If it was not changed in some later standard, yeah. And you may be able to do that as well. No, you are not able to do that, but you are able to not specify the arguments, but it is a deprecated feature and it is not advised to be used because it would not restrict the user later using the function as a library function on which type of argument to give to it, which may create some problems with security. Okay, don't do that. Just declare however you define it. Okay. So we've seen the global declaration and the local declaration, the local scope and the global scope. We also have an external scope, which is to say that we have a function inside of this lecture.h, and we want to use it inside of this lecture.c. By the way, h stands for header, and we usually do not include any definitions or maybe initializations, but no definitions of functions inside of header files. We just put the header files so that they are not occupying much space. They are just saying that declaring the functions that are to the including program that such a function exists, but they are not actually defining what's inside of them. We have libraries stored inside our operating systems, which is the job of the operating system, that would be able to find the actual definitions at the runtime for the program. So as you can see, we all have headers here instead of the stdio.h, and inside of these headers we only have the function declarations, not the definitions. The operating system, once this program is called, would locate where the object file, remember the name object file, for this library inside of your operating system is, and would load the function definitions to your program's data segment so that it is able to reach it in its runtime. But while compiling the program, to not make the executable occupying more space, we only use header files, which are only there to declare, not define. So like, for example, I may have a 100-line function here, and in the final executable, I will not have to include all of these and just would have to include this line. Okay, and the operating system would know to get the stdio.o so that my program is able to reach the code stored inside of this function as well. And if it is not able to find it, it would try to install it, or your program's installer would do it. In Mac and Windows, these are all done automatically, so you don't know anything about them. But if you're using Linux, you would be concerned a lot about the libraries, so you would know about these. Okay, so we have an external scope, and I have a function here, and I want to use it in some other file. By default, non-extern, and by that we mean global and local names, are not available for other files, including that is importing that file. But by declaring the names in the external scope, we can make them accessible by other files that are including that file. And by default, functions are extern, so there's no need to use the extern keyword at the beginning of a function declaration. But although you might just use it, it does not matter. But by default, the variables are not external, so you would have to specify that they're external at your header file, or whatever the file you're including is. By the way, you can also include an stdio.c, and you can also include a file in any name or extension. Extensions do not mean anything to the computer and to the operating system. It just tries to do whatever it is told to do with the files. The extensions are there for the user to be able to distinguish what a file is, but to the operating system, they do not mean anything. I have to say that. So the variable a is, let's say here, and let's do this. As you can see, what did I do here? The What was I talking about? I forgot. The functions are external by default. The variables are not, they're global. So we have to put a keyword at the beginning of our variable to mark it as an external variable so that the including files would know that would be aware, would include the name inside of their scope. And external keyword has a different meaning in C++, so do not get confused with it. And yeah, just I just forgot what I had to say. But yeah, this is basically it. We're just adding the integer a into the external scope of this file by using the extern keyword at the beginning of its declaration. So anything manipulating this a in some several files and its own file even would be visible to any other program, any other file that is also concerned with it. And at the end, when we are calling, let's do this. Okay. Now, you cannot make a global variable a local variable. In Python, you sometimes can do that, but in C, you cannot do that, okay? If you have declared the int sign to be global here, and you try to create a local of it, and which would be independent from the global int sign, you would not be able to do that, and then this int sign would be the same as this, and any manipulations you do to this would be done to this, and the same relation is present between the global and the external variable, so there is no priority list like local, global, and external as there is in Python. There's nothing like that, okay? Give me a minute, please. And by variables, we also pointers are variables and arrays are variables too. So they're included in all of our talks about variables as well. And sorry about that. So you might notice that and I think we can we can show something about the keyword of static, and then we would do something else. We would talk about an issue we are encountering here. But let's quickly mention about the static keyword. Like for example, the static keyword. Let's create another variable inside of this apt subtract. Let's call it a, not a, because a is already used. Let's call it a factor. Let's call it to be 1. And before returning it, let's add 1 to it, and let's make it here 0. And before returning it, we multiply this weird function right now because we have the word static at the beginning of it. What static would do here, that it would make the factor again in the local scope of this abstract function inaccessible from the outside, but every time uh, you call the function, the variable factor would preserve its value. And like, for example, in the first invocation of the factor, I would get factor to be 1, but at the second invocation of it, it would be 2 while returning it, because it would it would preserve its value. You can use this in some programs, although it is not thread safe. We're going to be talking about it more in our writing secure code with C lectures. But it is a useful feature to be sometimes used. And as you can see, factor is not global in the global scope. It's only in the local scope. But if we run the program, we would see what the what they yes. Let's see. This would work. I did not really read the error message. You should not do that. And it says something like relocation against C in function main, undefined reference to C. Let's just remove this line a little bit for our purposes, and then we'll come back to that later. So, and we're not printing the ABS abstract really. So, sorry, the inconvenience, but yeah. Then we're doing the same this as well. 4 minus 3 is this. As you can see, first it is 1 and then it is 2. How can this be possible? It is because the factor preserves its value throughout the invocations of this function. I'm distracted, so I cannot have the input. Why does it output so here? Okay. Why is the output 0? Yeah. So I was wrong about, as I've said, I'm not been programming in C, so I'm trying to teach all of the things from my memory. So I may be wrong sometimes, but if I'm wrong, I'm trying to correct it. So sorry about that. But the local global extern list is also in C. So if I declare it once more here in the local scope, the function inside of the function, when I try to access the variable sign, it would access the 1 inside of the local scope of this function. So it would be different from the 1 over here, which is in the global scope. So there's different variables that are in local and the global scope. So the same relationship continues with the extern. And you may ask, why did we have zeros when we, make the sign a local variable here when trying to print it in the main function? Why do we have zeros? Because the integer variables are initialized to 0 by the C compiler by default. They're initialized actually, but the initialized values are not stored in the RAM, so they say space by not initializing them. So this is more performance efficient than this, although it will not really matter in the modern machines much. But if you have some big array that is like hundreds of megabytes of size, you can have that, especially in the artificial intelligence project, which are usually not written in C. But anyways, you would be saving a lot of space in the RAM. So initialization does actually exist for the uninitialized variables, but they're stored in a different segment of the RAM, and the program would know that since they're uninitialized, their values are 0, but the program just would not store it. And if I am using the local sign here, if I'm specifying that the sign variable here is a local variable, then the global one would be ignored and no modifications would be made for the local one. They would not mix up. So the function that has the sign as a local variable to it would use its own sign, and the rest of the program would use the this sign over here, which is global, and the same relationship between the external and the global variables as well. So the priority list goes as follows. First, look for the variable, look for names in the local scope, then in the global scope, then in the external scope. So this is like so. And we've talked about the static, and you can also use static to make variables in a file invisible to the files, inaccessible to the files, including that file. And so it is just basically the reverse of what extern does. So keep in mind that if the static keyword is not used for something that is local, it would make it the reverse of extern. So keep this in mind. And let's see about our problem here. The problem that is popping up once we run this program, this line uncommented, and one I wanted to talk to you about. And it says user being LD. LD is the linker, and temp O. You can see that the compiler generated object files for this file in the process of compilation, and it stores it in a directory in my computer called temp, which is short for temporary, so it makes sense. Warning: relocation against C in read-only section text in function main, undefined reference to C. So undefined reference to C basically means we have no variable called C, but we have to be having that. If we were to remove this, then try to recompile that, it would work. So I guess the extern keyword does the opposite of whatever I told you it does. Oh, so okay. It does not do the reverse of what I told you it does, which would not make any sense. But you know, it is used in the file that is including it. So we have to be doing that in order to access the variable C here. Of course, we can access that without, you know, externing it in our file, but it using the keyword extern here would make sure that the compiler would search for other files this name so that it would not confuse it with if let's say it has the variable the name C inside of this file. Okay, so like so this has to work, and it does really. And about naming variables the same with other local other names in local and global and external scope. This is a really bad thing to do because it would make your code more unreadable, a lot more unreadable in reality. So don't do that. Give different names to your variables. You might say, well, how I would not confuse that in such a, thousands of lines of project. You would not, and for the most part, you would actually be double using the same names for different things, but they would be in so far different regions of the code that it would not make the reader of the program confused. Okay, so there's nothing wrong with that. And we have the concept of recursion, and it's a pretty basic concept, I think. So I would just make a quick example of how it works, and then we'll move on. Recursion basically means calling the same function inside of the same function. It is something like this. Like we create a function called int multiply, int actually power underscore, because I think it is defined in the math.h, or was it POW? Let's guarantee it. So it's A, it's B. By the way, the arguments to a function are also variables in the local scope of this function. So you can just as well change it inside the function. It would not raise any errors and it would work as expected. But no, just know about that. Okay. So, in real life, you would just do this, but because we want to understand how recursion works, and this is the only example that comes to my mind because I came unprepared, I would be solving the question of how to write a function that powers a number to the other by using the recursion. So I would just A is equal to A times B, no, A times A. I guess, let me think about it, if I can do this, if I can pull this off. Okay. Yes, with a little modifications here and there, and pull this off. Let's do like this 0, and let's shorten this to that, and this. Sorry, I'm writing really bad code. As I said, I have to get rid of this, my habit of coming to these lectures unprepared. And I guess I okay, this should work. This has to work. So let's write this out. 4 raised to the power of 3 is, I'm not trying to, verify whether it's or not. I'm just gonna run it and see if it works. And of course, we have to declare the function because without declaring the thing, anything would not be able to determine whether it exists or not, and we just throw an arrow at this. What? Okay, it gives an error because, or once again, I wrote the name wrong. Let's run this. So it does not work as expected. But why so? Why so? Why so? Four to the power of 4 is 64. And let me see. Oh, because we are, yeah, because, okay, because we are multiplying A with itself every time, and after the first iteration, A becomes the a becomes 64, and we're taking the square of 64 basically. So we have to have something like something like this as well, and so we have to something like this. It is equal to a. I'm just really complicating all of this so much, but I'm doing it for the sake of being prepared for lecture. And then this should work. Yeah, it works now. Yeah, it works now. I think you understand the code. It is a pretty complex and performance-wise low and very bad and unreadable writing of the function of power, but it works. Basically, what you have to understand is when I use the function, when I call the function inside of itself, it would just start executing itself from all over again, and it would just do this until it reaches a point of error, which is the maximum number of recursions, maximum number of calls to the function inside of its own function is reached, which is a very high number, and it is usually achieved by undesired and buggy behavior, not by your own design. Or it would just at the end have something like this, an endpoint where the function, ends without calling itself. In this case, it is this block of if, where it returns not the result of the call to the same function, but some definite variable here. And then it would, return that, the previously called function, and then it would take the result of this, return to the other function, and then the other function, and then the first calling instance would return that at the end. So we have to have a definite closing ending statement for the recursion as well. And what recursion means, once again, is calling the same function inside of the same function. I haven't really needed that much in programming, but sometimes it's a really useful and cool feature. You would know actually when you would want to use it. So I'm not giving you much examples here. And I guess we could move on to write a reverse Polish calculator here, because it's a pretty cool concept, which would first practice your programming skills while we're writing a sample program, and then we would link that pretty loosely to an important concept about programming, which would be useful in your real life programming experiences. So we will be doing that in the remaining of this lecture. It's about an hour, I guess. No, it's not about an hour. It's about half an hour. But we started half an hour after we started the meeting, which was half an hour after the usual schedule. So we're in some kind of different situation here, and so no problem. So let's delete all of that. Let's delete all of that as well. Vim is such a beautiful program. Okay, let's delete all of that. And so what reverse Polish calculator basically means, it's actually a notation, reverse Polish notation to, we use notations every day that we have as basically, or probably most of the humanity decided that this means 3 plus 4 in usual mathematical terms. This is a notation. We may denote 3 plus 4 with, let's say, this as well. We may have decided years and years ago, centuries ago, that this question mark would mean the word add, and these adding mark would mean the word question mark. So we chosen these all arbitrarily, or we used this mark of 3 to represent 3, but we could have used it to represent the 4 and vice versa. And we also decided as the humanity that adding an operator in between numbers would make the operator act on these numbers. So we decided that 3 plus 4 is written like that and not like, for example, this. Okay? Maybe we could have wrote that so that this would mean 3 plus 4 and at the end 7. But we decided, hey, we will put the operator in between the numbers we want to add. So this is a choice made by us humans arbitrarily, and we just made it. But in the early days of computing, some guy came up and thought, some other horrible notation would be better to be used in some other computers to calculate some stuff, and it actually saw pretty many uses, and it was received well by other people. So they just used it, and there's some notation now called reverse Polish notation, which I don't understand still because I have not researched much about the topic, but there exists something called it. It works by any number. By the way, the version we're going to be implementing today would only work for one-digit numbers, not to spend more time on doing this, and not because we cannot do that. It is it is pretty easy to implement such a thing, but we don't have much time. The reverse Polish notation works as you write a number, like you wrote a number here that is 3. It pushes into a stack. What stack means, as we've discussed in the previous lecture, you may think of a stack, the data type stack. We have a lecture in university called Data Structures and Algorithms, but anyways, a stack means you can think of them as a stack of books, and we have many books put on top of each other, and you first put this blue book at the bottom of the stack, and you just kept putting on more books on top of it, and then you reached this blue book on top of that. So you pushed all of these books. We call pushing. Uh, we call this pushing in the computer terminology. And if you want to get the books, you first need to take the one at the very top. And then after that, you have to take the one at the very next to that. You cannot take the one at the middle, like, for example, this blue, this purple or pink ones over here. You have to pick the one at the top of the stack. So this is how a stack works. You put data into the stack, and you can only get the topmost one, the most recent one, the one that you put there, most recently. You can get that before getting any others. So a stack works like that. So a Polish notation calculator would put the number that you give it to the stack. So our stack has 3 now, and then it would take the second number, because you've given a number, then push it onto the stack as well. And once it encounters a operator, which is the plus sign here, it would pop in line the numbers inside of the stack one by one. Of course, the first one and the second one, and it would operate on this by what that operator would mean, and it would converge into something like this. First, we popped the 4, we added the operator, which is plus sign, and then we popped the 3, and then we calculated the result, which was 7, and then we push that. We delete all of these from the stack, and then we push the resulting 7 into the stack, and then we continue. We encounter a 5, push it into the stack, and then we encounter a minus, and then we act on the operand, and we first pop 5, so there's 5 here, and then we add the operand, and then we pop the 7, so we have 2 here, and then we delete these and write 2. By the way, it's minus 2, yeah. I missed that. So it works like so. Okay, so we're going to be implementing this really quick. I won't be doing much explanation because I'm already writing slow code, because these lectures at the end of the day, my brain is not braining much. Okay. Sorry, just a minute. Just a minute. Okay, we are gonna be creating a stack, which is 1024 integers long. If you might ask, why did I choose that? It's because, it's a conventional number because it's multiple of 2, and 1024 megabytes, for example, is equal to 1 gigabyte. And all of these computer terminology, computer units follow that same rule. And we have a stack pointer, which at the beginning points to the beginning of the stack. Why did I initialize it to 0 before, even if it is already by default initialized to 0, to make it convenient? Because in some later, some reader of the code may not know that the stack pointer is initialized to 0, or some later versions of the compiler may not initialize them to 0. So this is no guarantee of stack pointer being initialized to 0. So we make it obvious to the compiler that we want this 0 at the beginning of our program. And stack pointer is the number actually that says where we are to push the next thing. Okay, it's like an index to the stack. So we start out by, okay, let's do this. This can be an interactive calculator. Okay, and then we can get a char. And let's find char here. And you may remember this syntax from our earlier lectures. Get char, maybe it was its name. Okay, its name is get char. And then if it's is not okay. Is numbered, maybe the stdlib. Up, and you're seeing the process of programming here. And is digit, yeah, its name is digit. Maybe we confuse them from different languages. Okay, so we minus that. You may remember the syntax from our previous lectures as well, and we push that to our stack. Okay, so we need to create a function called push, which we're going to be right over here, and digit. Remember, we only implement the 1-digit numbers here, and int push int digit, and then we say that our stack pointer is now the digits, and then we increment the stack pointer by 1, and we're not going to be returning anything actually, because to write faster, we are not going to be doing any error handling. If you would want to make a good program, you would actually return 1 or 0, indicating whether the pushing operation went to the plan or not. And if it did not went to the plan, the main function would do something about it, maybe inform the user, but we would not be implementing that right now. Potential out-of-bound access to the region with tainted index. What does this mean? I do not really know. And else, we're going to be switching into C. And if it is plus, we're going to be plusing, and then if it's gonna be this, we're gonna be subtracting, maybe minusing it. Okay, we're gonna be implementing these functions just in a minute. If it's multiples, we're gonna be multiplying them, and if it's a division, we're gonna be divvying them. And I guess this default and print f to the stdr that unsupported arguments, and we're gonna be turning on. Okay, I guess this is about it. So yeah, I'm really forgetting C. I hope I will relearn it in a while. Yes, it's plus, it's minus, it's mult, it's div, and conflicting types for div. So I guess there's a function defined somewhere in the libraries we include that are called div. So we're gonna be, why am I doing these typos? And fr printf, there's nothing called. So if printf we want, and okay, it works as intended. And what do we have to do? Maybe we return the maybe we return after an operation. No, not after an operation, just after the line is finished. We write down the result of the operation and the new line, and which would be the stack pointer -1. Yeah, that would be it. And we would implement first the plus, which would int a pop, int b pop, and push the a and b to the stack. And we're not going to be again returning any value here. And yeah, a lot of typos today, so we're going to have to implement pop as well. And we're going to be just doing stack. And as you can see, we're not also checking for whether the boundary of the stack is breached. We're not doing anything crazy here. Stack pointer -1. Yeah. Actually, we don't have to do that. We just have to, we can just change the stack pointer by 1, and it would be overwritten by the following values just as right. Okay, so we're going to be declaring that at the beginning as well, like so. And we're going to be changing that to void, and we're going to be doing that all of these. And okay, so we have to return. Yeah, I forgot. No, actually. Okay. Turn stack pointer. Okay. This is about it. This has to be it. Right? Yeah, this is it. So we're gonna be just copy pasting that, because programming is all about copy pasting, they say, which I pretty much agree, because programming is a honorable job, or at least it was. Nowadays it is being ruined by the laziness that programmers tend to, and I think which would not be fixed So we're just going to be mourning the good old days of computer programming and the scientific and the brain days of the old. So yeah, just gonna and let's run this. So I do this and we get an unsupported argument. Why? Okay, so we have a problem with which cases, I guess. Okay, we forgot the breaks. Yeah, once again, I'm forgetting a lot of things. So 1, 2, 5 minus, and we once again get the unsupported argument. Why? Oh, because we are not implementing this, right? We're not implementing white space. Just break them. Just do nothing. Okay. Just this. 1, 2. Okay. So we have to also implement this, I guess. As you can see, we're doing a pretty good job at correcting our mistakes. So I guess this should work, right? So yeah, result is 2. Is the result is 2? Yes, the result is 2. So let's try another one. Like for example, 4, 6, and the result is 0. Why? This mustn't be this. Oh, okay, we have to, I think, cast that int here so that it would also count the minuses as well. It does not. So why is that? Why is that? We're popping all of them. It is because of that. Okay, because I'm trying to divide them. No, I'm trying to minus them, but wouldn't give me proper results because why? Because why? Okay, so this works as expected, and this works as expected. No, the problem with this. Okay, so yeah, we made it not support the multi. So I remembered that I have to I have to. Okay, now it works. Okay, right. Okay, I have to get better at like remembering stuff. I'm sorry that I'm forgetting a lot of things, but I guess you understand what's going on in this code because it's a pretty simple code, I think. Can even break this down to uh, different files, like so. Do this, and we would also have to do this as well. And as we have learned in this lecture, would have to what? have to do that. And let's save this. Let's save this. What does it say? We redefine it. So I guess the definition means the same thing as initialization for the variables as well, because of the message we just saw about with the clang at the corner. So this is that. As you can see, we use the word extern, and even if your compiler does not require the usage of extern, you have to use it because I think it's a pretty important concept in that it is a it is signaling the reader of the code that this variable x is externed from some other file. So it is for the readability purposes and hopefully in the conventions of writing a program in C and different philosophies of writing programs, we're going to be talking more about that. So do you have any questions, and do you want us to continue with implementing file reading in this program so that we can talk about the idea of program arguments and terminal calling, or do we come back to that concept in the later lectures? What do you say about that?
I don't know. But
I'm asking whether you have time, whether you want to do that, because this has been an intense lecture. Maybe it's your brain is getting tired. I'm asking to you.
I think we can continue in the other lesson.
Yes, I agree.
Okay. Then
It was a tiring lesson.
okay, let me just give me a minute, please.
Okay.
I'm trying to note down what I just said because about conventional programming, because I will be teaching them in the later lectures. By the way, did you understand how this code works at on the screen?
Almost, but I can understand the extern what means. I think coach here.
Do you understand the general structure of the code?
Almostly, but I couldn't couch extern part. I couldn't understand extern.
Okay, just give me a minute. What do we call programming? Pragmatic? No, this is not it. Not the pragmatic programmer. The programming, what did we call the I'm trying to remember the name of a term. What did we call programming paradigms? Yeah. I'm going to be talking about this in later lectures as well. This is an important concept. And data structures and algorithms. So about the external keyword, you are
It includes or function.
what?
Is it include the I can say
Yeah, you can
Posting.
think of it as like so. It says the program that the name push, pop, the plus, the minus, mult, div, stack pointer is
Import
coming
this.
from another file. It tells it
Okay.
to use them as defined in another file, because if you did not use the extern keyword, it would probably look for them in the global scope, or just define them in the global scope, and the stack, the name stack here, would be different from the one that is here. Like the distinction between using a name as a local variable and a global variable, okay?
Okay.
Do you understand that?
Yeah.
Great. So I guess we're ending the lecture here. If you have not, if you do not have any further questions,
Yeah.
all right, see you then.
Okay. See you.
Bye bye.